Welcome back. If you've ever wanted a real under-the-hood look at how machines actually learn, you are in the exact right place. Today, I'm acting as your tech mentor for a special code-along YouTube tutorial explainer. We aren't just going to talk about high-level, fluffy concepts. We're breaking down exactly how machine learning algorithms learn, step by step, literally all the way down to the code.
I absolutely love this quote from our source material. It's hard to imagine a machine learning engineer who doesn't use Python. So if you waited for the right moment to start learning Python, this is that moment. It's so true, right? If you want to build real-world AI, you got to know Python. And that sets the perfect hands-on expectation for us today. We're going to get our hands dirty in the Python code to see exactly what a machine learning engineer actually does to train a model.
All right, here's our roadmap for today's explainer. 1. Anatomy of an algorithm. 2. Understanding gradient descent. 3. Coding it from scratch. 4. Upgrading the algorithm. 5. The pro-engineer way. And 6. Algorithm particularities. Let's dive right in.
Section 1. Anatomy of an algorithm. Let's look at the absolute foundation of what makes a learning algorithm tick.
Every single learning algorithm you're going to encounter is basically built on 3 simple pillars. First, you need a loss function. Second, an optimization criterion based on that loss function. And third, an optimization routine. This routine is kind of the engine of the whole thing. It leverages your training data to find the absolute best possible solution to that criterion. Now, interestingly enough, some of the older algorithms, like decision trees, didn't actually start with these explicitly defined. They were built on intuition, and the math just kind of followed later. But in modern machine learning, these 3 steps are absolutely your gospel.
Section 2. Understanding gradient descent. If you've read literally any modern literature on machine learning, you've definitely seen this optimization routine pop up.
So, gradient descent is basically an iterative optimization algorithm used to find the minimum of a function. The best way to visualize this? Imagine you're taking steps down a really steep hill trying to find the absolute lowest point. You start at some random spot on the hill, and you take steps proportional to the negative of the gradient, or, the slope at your current point. We also need to define a really crucial term here, which is an epoch. An epoch is just one complete pass through all of your training examples. You usually need quite a few epochs before you reach the bottom of that hill. To make this super concrete for our tutorial, we're going to build a linear regression model. We'll use a real data set to predict sales, specifically the units sold based on how much a given company spends on radio advertising.
Take a look at the data we've got here. We have 200 training examples representing 200 different companies. The x-axis is the radio ad spending in millions of dollars, and the y-axis is the sales in units. Our goal with gradient descent is to find the optimal straight line that cuts right through the middle of these points, minimizing the mean squared error. Basically, we're trying to find the perfect slope and the perfect intercept. Section 3. Coding it from scratch. Okay, let's roll up our sleeves and see exactly what it takes to code this whole learning process from the ground up.
If you look closely at the loop in this Python code, you'll see where the real heavy lifting happens. We aren't going to read every single line, but notice the mechanics here. We are actually using calculus, specifically the chain rule, to calculate partial derivatives for our parameters right inside that loop. We initialize our starting point at 0, and then we iterate through our training examples. For every single example, we update our line's slope and position using a learning rate. Think of the learning rate as controlling the size of our step down that hill. We just keep looping this through multiple epochs until the parameters basically stop changing.
So as that Python code chugs along through thousands of epochs, it slowly decreases the average loss. But what does that actually look like visually as the machine is quote-unquote learning? Oh, this is the ultimate visual payoff right here. Notice what happens as the algorithm learns. At epoch 0, the line is wildly off. It's essentially flat at the bottom. But as we move to epoch 400, then 800, the algorithm is taking those calculated steps down the hill. By epoch 3000, it has pulled that wild line perfectly into place to fit the trend of the data. The average loss drops from over 92 at the start, all the way down to around 19 by the end. The machine has literally learned the relationship.
Section 4. Upgrading the algorithm. Seeing that line snap into place is awesome. But standard gradient descent has a bit of a flaw. It can be super computationally heavy for massive datasets. So here's a quick pro tip. You'll rarely see plain vanilla gradient descent in modern neural networks. Instead, these variants are what the pros actually use.
Stochastic gradient descent, or SGD, speeds things up by approximating the gradient using smaller batches of data rather than the whole data set at once. Then you've got attegrad, which scales the learning rate for each parameter based on its history. Momentum helps accelerate the descent in the right direction while reducing those annoying oscillations. And finally, variants like RMSprop and Atom, those are the absolute workhorses powering most modern neural network training today.
Section 5. The Pro-Engineer Way. Now that we've done the grueling calculus and the explicit coding from scratch, it's time for a massive release of tension. Let's see the professional shortcut.
Look, unless you're a research scientist, you generally don't sit around writing the math yourself. You rely on open-source libraries that are implemented with incredible stability and efficiency, like scikit-learn. Just compare these two approaches. Instead of explicitly calculating partial derivatives and tracking thousands of epochs, you simply import the model and call .fit on your data. Building and training the model takes literally 3 lines of code. It just works.
And here is the absolute proof. Whether you ran our complex 15,000 epoch from scratch code with the massive calculus loops or the 3-line shortcut, the result is identical. If we ask both models to predict the sales units for a $23 million ad spend, both predict exactly 13.97 units sold. No difference whatsoever.
Section 6. Algorithm Particularities. Before we wrap up this YouTube tutorial explainer, let's quickly rapid-fire through a few algorithm differences you should know.
Think of this as a quick checklist of gotchas for junior developers to watch out for. As you explore different models, keep in mind they behave really differently. First, you got to tune their hyperparameters, like that step size we talked about. Second, they eat different types of data. Some handle text totally naturally, while others demand pure numbers. Third, watch out for skewed data. Some models let you weight minority classes to avoid misclassifications. Fourth, always check their outputs. Are you getting a hard category or a probability score? And finally, some algorithms train iteratively in small batches, while others demand your entire dataset all at once.
You now have the foundational knowledge of how machines actually learn, step by step. You've seen the math, you've seen the from-scratch Python code, and you know the 3-line pro shortcut. So the crucial question for you is, what problem are you going to solve next? Thanks so much for joining me on this explainer, and happy coding.